The extrinsic semiconductors which you have studied till now are usually doped with either acceptor impurity or donor impurity. But compensated semiconductors are those semiconductors which are doped with both type of impurities. We are having conventional energy Venn diagram in which we have EC, which is the minima of energy band level of conduction band. We have donor energy level ED, acceptor energy level EA, and maxima of valence band energy EV. Now you have to look very carefully. You know that if we have donor concentration ND, then few of the donor atoms have absorbed sufficient energy so as to release an electron from donor energy level to conduction band, leaving behind ionized donor atoms represented by Nd+. And this portion which is not ionized, it means that electrons are still present at this energy level. We will represent it by Nd, and the total concentration will be equal to Nd. Nd is equal to concentration of ionized doping atoms plus concentration of electrons present at donor energy level. The same can be done for acceptor energy level. Few of the electrons from the valence band will excite to acceptor energy level, leaving holes in the valence band. This concentration of ionized acceptor atoms can be represented by Na- and the unionized acceptor impurities concentration can be represented as Pa, which in other words can also be said as the concentration of holes present at acceptor energy level, and the total concentration will be Na. Na is equal to Na negative plus Pa. These are the electrons which exist due to the result of ionization. Similarly, we will assume that there are few electrons which will be naturally present due to the temperature, and the overall concentration of all these electrons will be equal to N0. Similarly, we will assume that the holes which we have represented here is the result of ionization, and we also have few other holes which are caused due to the temperature only, and the net concentration of holes is P0. By the principle of conservation of charge, we can say the semiconductor will still be neutral, meaning that the total charge on the semiconductor as a whole will be 0. Or in other words, you can also say that positive charge is equal to negative charge. Sometimes this condition is also referred to as charge neutrality. Now for positive charge, we have P0, which is the concentration of holes in the valence band, and we have Nd+, which is the ionized donor impurity concentration. Similarly, for negative charge, we have N0 plus Na negative, which is the concentration of ionized acceptor impurity. Also, we can change this equation by replacing Nd plus and Na minus. We came to this equation by using these two equations. This is the most basic formula in which we have not assumed any approximation so far. And also, you know that for an non-degenerate semiconductor, we have mass action law which says N0 into P0 equal to Ni square. Now assume that the doping concentration, the concentration of electrons at donor energy level, and acceptor concentration as well as hole concentration at acceptor impurity level is provided, and you are asked to find the value of N0 and P0, then you have to use both these equations to find a quadratic equation, and after solving that you will get concentration of both free electrons and holes. So it is very important to remember that this is the most basic equation in which we have not assumed any assumption or approximation. And by using both these equations, you can find the concentration of free electrons and holes in an compensated semiconductor if the value of other variables are provided. Now, we will assume complete annihilation has taken place, meaning that ND is equal to 0. Similarly, PA is also 0. So, the charge neutrality equation will reduce to P0 plus ND equal to Na plus N0. Now, we will put P0 equal to Ni square divided by N0 in this particular equation. Then, we will get so we end up with a quadratic equation which will give us two roots. After solving, the two roots of N0 will come out to be like Nd minus Na divided by 2 plus minus Nd minus Na divided by 2 whole square plus Ni square. Since the value of free electron concentration cannot be negative, so the negative term will be eliminated, giving free electron concentration to be equal to and this is the final answer. For getting this value, we have assumed one approximation, that is, the complete annihilation has taken place, and other, which is an important condition, is that the semiconductor is non-degenerate type, meaning the doping concentration and acceptor concentration is significantly greater than intrinsic concentration as well as fairly smaller than effective density of states Nc and Nv. By similar analysis, you will find the value of P0 to be equal to Na minus Nd divided by 2 plus Na minus Nd divided by 2 raised to the power 2 plus Ni square. Now we will come back to our free electron concentration and we will assume that if it is normal n-type semiconductor such that acceptor impurity is 0, then we will have the formula for free electron concentration to be Nd divided by 2 plus Nd squared divided by 4 plus Ni square. We have simply removed Na term from the previous equation. This is the exact formula for free electron concentration when we are having normal n-type semiconductor which is not having acceptor impurity and the temperature is also sufficiently high such that complete annihilation has taken place. Now we will put the third approximation, which is Nd is significantly greater than Ni, meaning that Ni square can be neglected in the under root expression, giving us free electron concentration to be equal to approximately doping concentration. In the last lecture, in which we have assumed the majority carrier concentration of an extrinsic semiconductor to be approximately equal to the doping concentration, then we have actually assumed three approximations which are described in this lecture. And by applying mass action law, we will find minority carrier concentration, which for an n-type semiconductor is P0 equal to square of intrinsic carrier concentration divided by free electron concentration, which is approximately equal to doping concentration. But you should remember this particular formula also, as sometimes just to check your basics, Questions can be framed in which ND is comparable to NI. Like, assume ND is given to be equal to 8 multiplied by 10 to the power 10, whereas Ni is equal to 10 to the power 10. In such cases where ND and Ni are not much different, then you cannot apply the approximated formula. You have to solve by using this equation. Generally, ND is of the order of 10 to the power 16 and Ni is of the order of 10 raised to the power 10. In such cases, when Nd is significantly greater than Ni, it is okay if you put the free electron concentration to be equal to doping concentration. It is okay to use the approximated formula if doping concentration Nd is greater than or equal to at least Ni multiplied by 1000. I hope all the points are clear to you and you can put different approximations as per the data which is provided in the question.